Hi, this is Kjetil. This is a lecture that deals with chapter 11.1 and the so-called advanced modeling of the synchronous generator models, which are the models that we use in our studies, and also introducing the Park transformation and complete dynamic models. Now, this could have been the first lecture in the course since it deals with the basic modeling. But since this course is about power system stability and control, and that we assume that you have some knowledge on electrical machine, it makes good sense to start with a simplified derivation of the machine models as it is done in chapter 3 and 4. The chapter 11.1 makes a more fundamental mathematical derivation of the synchronous machine model, and it also formally sort of introduces and explains the Park transformation. This is usually the final lecture in this course, and normally we don't ask too many questions about it on the exam, but it is, in my opinion, 4 important points that you should remember, and these are listed here. Number 1, Park transformation results in time invariant inductances. Those are the direct and the quadrature inductances and reactances and so on. And it explains why they are time invariant. Number 2, flux linkages are decoupled in D and Q axis, which is a very nice property. Number 3, power can be easily expressed in terms of the D and Q axis voltage and currents. And the point 4, expression for the induced voltages in stator becomes simple, simply saying that the induced voltage in the D-axis is proportional to the Q-axis component of the stator flux multiplied by the speed, and vice versa. So what is the ambition level of this lecture and this chapter? I would say it's first of all that you could keep track of the major steps in the derivation of the model and see the advantages of using the transformations and sort of understand why we do end up with the D and Q axis representation and why we need that. You also have some understanding of how we integrate generator and network equations, so to build up the final dynamic simulation models in a way that is implemented, for example, in Power Factory. When we do a mathematical derivation, we always make some assumptions. These are the most important assumptions in this context. We assume that the 3-phase stator windings are symmetrical. We ignore the capacitances of the windings. We also say that each set of windings is represented by one concentrated winding. Of course, in reality, these are distributed somewhat in space. We also say that the change in inductance due to rotor position is sinusoidal, and we come back to that in more detail. We say that in transient and subtransient state, and when developing this model, we say that the rotor speed is near synchronous speed. That may look like a contradiction, since when we study power system dynamics, we are very much interested in the variations of rotor speed and frequency. But when we derive the model, we say that the rotor speed is constant in a way. So that's, you can think about that. We say that the magnetic circuits are linear, not saturated, and that hysteresis losses are neglected. Now, this is the way we consider the synchronous machine with 3 sets of windings in the stator that are 120 20 degrees separated in space in the machine. And we have a rotor where we have the main field winding, and we have also two windings that represents the damper windings. And for simplicity, these are placed then in the D and Q axis respectively. The rotation is assumed to be synchronous and can be represented by the gamma, which is the omega times time. Now, the first we do is to set up the relationship between flux linkages and the currents in each of the windings. And since there are 6 windings, we end then up with a 6 by 6 matrix of inductances. We could write this in more compact form by separating the windings and the currents in stator and rotor as is indicated here. Basically, I mean, all the currents influence the flux in all windings. So basically, we could imagine that this is a full 6 by 6 matrix. But one of the challenges is that most of these inductances, they change with time, which is due to the saliency of the rotor and the rotation as such. And we will describe a little bit why it is so. First, in the book, it's listed how we model each of the inductances. And if we look at the self-inductance in each of the stator windings, it can be represented by a constant term and one term that vary 2 times in one rotations. And the mutual inductances between the stator windings, the flux linkage that is set up by the current in stator winding B on the flux linkage in winding number A, for example, has the same structure but with a different sort of starting angle. Now, why are the self-inductances varying? This is my very simple understanding of that actually. Now, the inductances are the relationship between flux linkage and current, right? And the inductances, as we know, they are basically proportional to the number of windings that they link and that they are themselves, and the reluctance. So if we look at the different positions of the rotor here, let's assume a rotor like this, and the flux set up by the current in stator winding A will sort of link like this, right? And what determines the reluctance in this position is the air gap here. But when, for example, the rotor has turned 90 degrees, it's the same representation, but the air gap is larger in that position, so that the higher the air gap, the higher the reluctance, and then the lower the inductance becomes. Now, why it varies 2 times per rotation is, of course, because it doesn't matter which way the rotor is. It's just the position in a way. It's not the orientation of it. Next, we need to look at the mutual inductances between the stator and the rotor windings. And they vary more because of the position. And if we look at flux linkage set up by the main field current, for example, and linking the stator windings A, we could say that it's proportional to the cosine of the angle. And that also goes for all the other mutual inductances, but with differences in starting angle naturally. And as always, the maximum occurs when the axis of the stator and the rotor windings align with the same positive flux directions. And it can be sort of illustrated in the same way. The same simple drawing as before. Just that now we need to indicate the field windings, right? Setting up a flux that in this position completely links the stator windings. And then as the stator moves and come to 90 degrees, for example, it will effectively sort of the flux compensates for each other, so there will effectively be no flux linkage. So then this is 0, and turning another 90 degrees, it will become the opposite direction, so it goes negative. So that is my simple understanding on how the mutual inductance between stator and rotor behaves like a cosine function. Then it is time to introduce the Park transformation. And in this setup, it is indicated as the transformation from stator quantities in A, B, C to D and Q axis quantities. And we see that it's a time varying transformation as it depends on the position of the rotor. Now it can be written as a 3 by 3 matrix when we also add the zero sequence of the currents or voltages as the sum, being the sum of the 3. There are these beta factors. There are some that sort of arbitrary, but there are some choices that are better than the other to make the transform symmetrical in a way. So we represent the Park transformation as the matrix W, and it is used to transform from stator quantities to 0 dq quantities. So the complete transformation involves the stator to rotor to the dq axis only, like shown here. Now, if we make this transformation, the point is to transform to dq, right? So if we start with the upper left part, the C, let's call it the C ABC, equal to LSR times I ABC. We transform to 0 dq quantities by the transformation, and then also transforming the currents. We have 0 dq equals times LSR times the inverse to get to 0 dq. And that is what is indicated in this final matrix here, that how this is transformed between all of the variables. And you also see that the point with the beta constant being square root of 2/3 is that it makes the inverse of the Park transformation equal to the transpose of it. So then if we do this matrix multiplication, multiplying the Park transformation by the self-inductance matrix times the inverse of the Park transformation, we end up with first a diagonal matrix and and also a time-independent matrix. So that is sort of what we wanted to show in point 1, that the Park transformation gives time-invariant inductances, and we call this the d-axis and the q-axis inductance or reactance. Now, if we look at the mutual inductances between stator and rotor, we obtain those by the same transformation, and what we find here is that they are also time independent and as well decoupled in the Q and D axis. So with all this, we could put up the complete description of the flux linkages in the DQ framework. And as we see, we can split it up in this way, and we also see that you have the decoupling in the D and Q axis. So this is then the same picture as was presented in this in chapter 3, I think, where the fictitious windings that result from the transformation can be seen lying in the D and Q axis. And the zero sequence, of course, doesn't play any role as long as the currents and voltages are symmetrical. So that was point number 2 to remember. Flux linkages are decoupled in D and Q axis. The third point is quite straightforward, so I won't spend any time on that. You remember the way of computing power by multiplying voltage, phase voltage, and phase current in all 3 windings. And if you apply the transformation, you obtain a very simple and corresponding representation by multiplication of the voltages and current components in the D and Q axis. Assuming symmetry, a sort of V0 and I0 would be 0. So that was point 3. And then the fourth point is perhaps the most difficult to explain. Here we start with the induced voltages as they appear as being proportional to the rate of change of the flux linkages. And of course the loss term, which is kind of trivial. but it's the rate of change of the flux linkages that is interesting to study. So from this general model of the voltage induced by a winding, we look at the stator voltages, the V, A, B, C if you want. That is proportional to the rate of change of the fluxes A, B, C. Now we apply the transformation, so we get the D and Q voltages being equal to the product of the transformation times the rate of change of C, A, B, C. But then we have to transform the fluxes. So we have V0 dq equals minus W times d dt of the inverse transformation times C0 dq. And here we have the point that we have a derivation of a product of the inverse transformation matrix and the fluxes. The derivation of the products are shown here, so that our voltages V dq equals then W times, if we start with the other element here, times something that is proportional to the derivative of the flux linkages, plus something that is proportional to the rate of change of the transformation and the steady state dq fluxes. So we see that there are two components coming in here, and we need to evaluate then the product of the transformation times the inverse of the transformation. This is the interesting part. And you can do that yourself, and if you do it correctly, you will find that the answer becomes very nice, because it's basically most of the elements are 0 and a couple of 1 and minus 1. So when we put this together, we find that the final model of the induced voltages is consists of 3 terms: the trivial voltage drops due to losses, resistances, and the transformer terms that are proportional to the rate of change of the fluxes, and a term here that is due to the rotation. So, and this is an important finding, because it shows that the induced voltage is proportional to the rotation of the machine. So this was point 4. In a way, the expression for induced voltages in stator becomes simple, and if we ignore the rate of change term, which we often do, it says that the induced voltage in the axis is proportional to the flux linkage in q axis, and induced voltage in q axis is proportional to the induced or the flux linkage in the axis. Now, one could discuss these equations a little more, and if we write them out, we see the equations here for the stator, and very often what we do is we neglect the rate of change terms here, because they die out very fast, and we have then 2 equations describing the stator voltage, and we have three differential equation describing the flux linkages in the field windings. And this is with the damper winding models. Of course, if we do not explicitly model the damper windings, we end up with one differential equations, as also is discussed in chapter 3. So now we're back to that model in a way, and the final equations is listed here with the note that we have neglected the stator dynamics, as we usually say. And then it's the same derivation as described in chapter 4 on how to go from the flux description till the description that we usually do with the internal transient or sub-transient voltages. And these are listed here. I won't go into detail in describing them. And if we do that, we are back to the equations or the model that we have been using in this course. Then also you could do the same with the fifth order model, and this corresponds then to having modeling two windings for the damper windings. And there's also another version with the sixth order. And this is the final sub-transient model as we are using it. But now we have the formal derivation of these equations. The third order model, which we discuss in detail, the fourth order, and we also have, if we neglect the dynamics of the main field flux at all, we end up with the what we call the classical model. Now I have added a few slides on how to integrate the generator equations to build up a complete power system model. And this is for when implementing these models, this is perhaps the most difficult part. In this representation, we have used the phasor concept for currents and voltages, loads represented as impedances or constant current. You can also assume that there could be constant power or a combination. But other components are interfaced as current injections. As long as we represent the loads as impedances or constant currents, we can use the admittance representation of the network because all the components then are added as current injections. This is the way to look at it that I used to. It's my understanding, at least. If we have, for simplicity, a two generator model, what we could do is to first sort of detach the generators, which represent the dynamic components, and you're up with the effect of the generators as current injections, right? Then you have an admittance representations of the network. And that network can be described like this, using the same, the well-known formula for representing the admittances. And then what we do is we assume that the generator is modeled as a voltage source, transient or sub-transient source behind a reactance. And the reactance if we go from the sort of the Thevenin representation down to the Norton representation, we can add these reactances into the network model. So and that comes in on the diagonal elements where the generators are modeled, and then we have a representation of all the reactances or possibly resistances, and we have an expression of the current injection being depending on the internal transient voltage in this case then. So then the final model will be to link the dynamic equations with the algebraic equations. And then one has to keep in mind here that the internal transient voltage is usually modeled in the reference frame of each generators. So it has to be transformed to the correct angle, which is in this case then the angle between these machines. And you transform back to the machine reference to obtain the currents IQ and ID that is needed into the dynamic equations. Because you see the dynamic equations depends on the ID and on the electrical power. And those depend has to be computed in their own reference frame. When you do that, you get a sort of a general flowchart of dynamic simulations like this. You initialize. You do that in Power Factory by pushing a button. But what it does is that it finds the initial values of all the state variables. In this case, it's the internal transient voltage, the angles, and the speed. Then you need to define some events. Any change in load, a short circuit, etc. that impacts the admittance matrix. And from the initial value, you compute the current injections. Having the current injections, you compute the voltages on all nodes. When you have computed the voltages, you can compute the generator currents in the global reference frame. But then you need to decompose that current into the reference frame of each generator in order to get the d-axis current and the electrical power. When you have done that, you have all the input to the differential equations, and you can do the numerical integration and do the time increment, update the state variables, and go to the next time step, etc. So that's very simply how a power system simulator works. So to sum up, the last slides on complete models was more for your information, I would say. But these 4 points that's listed, I think it's very relevant to remember that the Park transformation gives time invariant and decoupled inductances. It makes the LD and LQ, etc. The flux linkages are decoupled in D and Q axis. Power can be easily expressed as the product on voltage and current in each axis. And the expression for induced voltages in stator becomes very simple as shown here. So thank you. This is it.